In this video, we're going to talk about how to quantitatively determine how similar two distributions are to measurements with uncertainty. And we're using distributions as sort of a placeholder. So if you think of the mean of the distribution as A, or the average A, and its uncertainty delta A, which might be a standard deviation, then this is a representation sort of what error bars would be if this is A, and then delta A is the distance to the edge. So one way that people often talk about agreement between data points is whether means overlap. So if this one is B with its uncertainty delta B, then one thing to look at is, do the error bars overlap? But just sort of this binary comparison of overlap or not ignores the fact that there is some overlap in here in the tails of the distribution. So we want to try to characterize that somehow. So one way to look at this is to turn this into a continuous number rather than just a binary decision. So we can think about the difference between the two means, but we want to do it in units of uncertainty, so that it's now a fraction that looks at how different is it in units of uncertainty. And we're going to square this for reasons that are beyond this video, and then take a square root. And so this structurally is similar to what you may have seen in statistics classes, sort of student's t-value, but student's t requires that the measurements be means, sample means, and standard errors of the mean. But we're going to use this for any measurement and its uncertainty, so we're going to call it t primed for the time being. So if we put look at our t primed equation up here, there's some things that come out of this index, this number that comes out. So for example, if t is less than 1, then that means that the difference on the top, the numerator, is less than the uncertainty, which means the measurements are closer to each other than the size of their uncertainty, which suggests agreement. But it could also just, this fraction, right, can become as small as you want if you make your uncertainties as big as you want. So it could just be overestimated uncertainty. So large uncertainties, bad precision is hiding a small effect. If t is greater than about 3, then that means the difference between the two means is greater than about 3 times the uncertainty, which suggests they're probably different. The numbers might disagree, or you might have made a mistake. There may be a systematic error somewhere, or there could be something physically going on that you hadn't seen before. And then if it's somewhere between 1 and 3, we just sort of say that that's in tension, and it's unclear whether it agrees or disagrees. And so in all of these cases, the thing to do is going to be to get better data. So in the first case, when t is small, since your uncertainty might just be too big, you should go and try to figure out if you can get your uncertainty down to see if you've just hidden an effect by poor precision. And if they're different, this is assuming that they should be the same, then the difference suggests that something's wrong and you should go back and try to improve it. And if you're somewhere in the middle, then it's unclear, so you should go back and get better data. So this is what we're going to be using to compare measurements with different uncertainties for the rest of the lab. Cool.